Alright, still in unit number 2, working through example number 9 on page 11 of your notes, and we just learned the previous lesson. We just learned basically how to derive the big three. We didn't learn how to use the big three. We just figured out where it all came from, where the big three came from. So in this video, we're going to spend some time looking at how to use them. And when we use the big three, we're always going to start off with 5 ideas. We're going to start off with distance, or better yet, displacement, initial velocity, final velocity, acceleration, and time. 5 things every time. So when you think of the big three, you got to think of 5 things. And if you were in class, what we would do is we would have a student hop in his or her car. We'd go outside and go to the road. Have that student be at rest in their car, and so here it is here. Ooh, the car's upside down. That's not good. All right, so there it is. The student would be at rest in their car, and the car would be at rest as well. And then basically lay on the accelerator, and we would time how long it would take that student to go a certain distance, maybe like 100 feet. And then from that, we would use the big three to calculate the acceleration of the car. And so, since we're actually not doing this on doing that in this video, I'm going to make some numbers up and just kind of work it through a little bit, but you get a feel for it. So here it is, acceleration of a car, and we're going to go 100 feet. So the distance that we travel is 100 feet. Our initial velocity, because we start out at rest, is going to be 0 meters per second. We don't know how fast we're moving at the end. I guess the driver could look down at their speedometer when they cross the finish line and see how fast they're traveling, but we want to be safe, and we want the driver to be, look at the road at all times, not take their eyes off the road. So we really don't know what the final velocity is. We don't know what the acceleration is because we want to know that. That's our ultimate goal. And then time. We don't know time, but what we would do is we would have some students measure the time. And since we can't really do that in a video like this, I'm going to give you a time. So we're going to say it's going to take about 8 seconds. And that might be a little longer than normal, but that's okay. We'll get the concepts here as we move along. All right, so the first thing we got to look at is when you're using the big three, we have to write these 5 things out. And here's the rule of thumb. Rule of thumb says this. If you know 3 of those 5, so here's the 5. If you know 3 of them like we know them, then you can use the big three to figure out the other 2. Let me say that one more time. If you know 3 of the 5, you're home free. If you know 3 of the 5, you're home free. You can use the big three to figure out the other 2. And that's what we're going to use. So I'm going to pull in my equation sheet, and this is where you need to get familiar with the equation sheet and be able to find them. I need to be able to see. I want to know acceleration, and I don't know final velocity. So I'm going to look for an equation that doesn't have final velocity because I don't know final velocity, and so it doesn't make any sense for me to use an equation that has final velocity in it. So this one has final velocity, so I don't want that one. Look at this guy. This guy does not have final velocity in it. This one does. This is the one I think I'm going to use. So I'm going to go ahead and rewrite that guy. So that's d equals VOT plus 1/2 AT squared. All right, couple things when we're doing equations. Number one, you always have to rewrite the original equation. Never, ever an exception to that. So you always have to rewrite it. It'll drive you crazy, but later on, you'll thank me for it. And then I always put a line through my equal signs. That's just kind of I teach algebra, and it just helps algebra students learn how to pick the concept up. And so it's just kind of a crossover from when I teach algebra, but I think you'll appreciate it as we go along. All right, your initial velocity is 0. So this whole term right here, whatever your time is, it's 8, because it says 8 down here. But 0 times 8 is going to be 0. So what I do is, if it's 0, then I just put a little line through it and to show that this whole term becomes 0, and I don't have to really worry about it. Okay, now the goal of this is to figure out the acceleration. And to do that, I know most of us are really used to just plugging numbers in and solving the equation. But in physics, we want to do it in reverse. We actually want to solve the equation first and then sub numbers in. And this is another one of these things you're going to kind of not like at the beginning, but come January, February, March, April, May, you'll start to love doing it this way. It's going to take several months for you to kind of get used to doing it. So I'll do it slowly for the first couple times, and then move a little quicker as we go through other problems. Okay, so the first step is we want to solve for a. So to solve for a, I'm going to multiply both sides by 2 because I need to be able to cancel that 2 out there. So then I'm left with 2d equals at squared, solving for a. To solve for a, I'm going to divide both sides by t squared. So then I get a is equal to 2d over t squared. And now I plug numbers in. So my 2 here, my distance was 100 feet. Now I got to make a conversion because I've got feet and seconds and I don't want it in feet and seconds. I want it in meters. So I'm going to come back up here and I've got 100 feet. I'm going to do a conversion. So 1 foot is 12 inches. 1 inch is 2.54 centimeters. And then 100 centimeters is 1 meter. And I'm going to plug that into my calculator. And so 100 times 12 times 2.54 and divide by 100. And there it is, 30.48 meters. I'm just going to round that to 3.5 or 30.5. So 30.5 meters, all divided by the time, which was 8 seconds. Don't forget to square it. I'll plug that into my calculator so you can see how that's done as well. So we get 2 times 30, 30.5. And then on this 8, I divide by 8 twice. And I'll do it the other way and see if we get the right answer, but that's the best way of doing it. And I get 0.95. Now, what are the units on this? This is where plugging units in is always going to be real helpful, and you're expected to plug units in every time we do an equation like this. And you look at the units, it shows you right here. So it's meters, and then there's a second squared, so this is going to be meters over a second squared. Should it be meters per second squared? Absolutely it should be meters per second squared because it's acceleration. If we came up with something like meters per second, time out. We made a mistake. So a lot of times if you let the units guide your thinking, you can kind of see if you made a mistake along the way. All right, I told you I'd actually calculate this a little differently. Some people take this and multiply by 30.5, and then they divide by 8 and then multiply by 8. And I'm kind of curious to see what this gives us, because this particular, yeah, see, we don't get the same thing. So you have to be really careful on this. The best way of doing this is to go 2 times 30.5 and then divide by 8 and then divide by 8. You gotta divide by 8 both times. Notice the difference right there. That's where it's going to get you. And the answer is 0.95, about a meter per second squared. Okay, moving along. We also have a part B to this, and I think I've lost my article on this, so I had to look this up online, and I'm just going to share a little bit about it. There's a car out there that has a very, very quick acceleration, and it's called a Bugatti. And if I've got the name pronounced correctly, it's a very, very expensive car, but it has an incredible acceleration. And our goal is to figure out what that acceleration is. And I looked up online some of the specifications of this particular car. It can go from 0 meters per second to 100 kilometers per hour. Now that's about 60 miles per hour in 3 seconds. And I basically went online and researched that a little bit and take but a couple minutes and found that. And from that information, we're going to calculate the acceleration of that particular car. And we're going to go back to the equation sheet. Now, remember the rule. The rule says this: if you know 3 of the 5, you're home free. Well, I do know 3 of the 5. So I'm going to go to my equations, and I'm going to try to find an equation that doesn't have distance, because I don't know distance, so anything that has distance I don't want to use. Well, the third one and the second one both have distance, so I don't want those. I'm going to use the first one. So the first one is VF equals VO plus AT. Notice the initial velocity is 0, so I can cross that out like I did on the previous problem. I want to solve for the acceleration, so divide by time. So acceleration is VF divided by T. All right, and then it's going to plug stuff in. But before I do that, I need to convert kilometers per hour to meters per second. So there's kilometers per hour, and I know that there are 1,000 meters in every kilometer, and every hour is 3,600 seconds. I'll plug that into my calculator and do it so you can see it as well. So I have 100 times 1,000 divided by 3,600, and I get basically a number that doesn't make a lot of sense to me. Did I do that? I was thinking right around 60. So this is 277. I was thinking miles per hour. That's what I was doing wrong. All right, so 100 kilometers per hour is roughly, in terms of miles per hour, 60. But in terms of meters per second, we're going to round that off, is 278 meters per second. Let's make sure I didn't make a mistake on that. So we've got 100 kilometers per hour, 1 kilometer, kilometers cancel. There's your meters on top. Hours there. Yep, that's good. So, and I did my calculation correct. So there it is. So I'm going to say about 278 meters per second. So 278 meters per second. And when I looked it up online, it had a time of 3 seconds. So I'm going to come over here and divide that. So divide that answer by 3, and we get 92. Something looks fishy. Something looks real fishy about this. 92, or about 92.6 meters per second squared, and that's the acceleration. And that, I know, is not, I don't think that's right. Well, it's either I looked up a wrong number or did something else that was wrong. Give me a second while I look up online. From 0 to 100 kilometers, I'm looking right up online right now. It says 3 seconds. And did I do anything wrong on my numbers? So there's 100 kilometers per hour, 1 kilometer is 1,000 meters. And let's try that calculation one more time, make sure I didn't lose a 0. Now I saw it. You probably saw it on the line. I had an extra 0 right there. It should only be 1,000, and I plugged in 10,000. I knew something was fishy. All right, so 100 times 1,000 divided by 3,600. And there it is. So it's going to be 27.8 meters per second. Something wasn't right there. So this will be 27.8, and then this will be, that looks more reasonable, which is kind of a good lesson for us. So it's going to be about 90, what? 9.26 meters per second squared, which is a good lesson for us. A lot of times when you're doing calculations, do the calculation, step back a little bit, look at it, and see if it actually makes sense. If it doesn't make sense, then you probably did something wrong, and you probably need to backtrack and figure out what you actually did wrong with that particular problem. All right, very good. We're going to flip the page. And I guess before I move on, let's compare these real quick. So this is maybe just a typical car. If you look at this actually the acceleration, that car we did in part A really wasn't very big, so about 1 meter per second squared. This is about 9 meters per second squared. And let me just translate that to you. This is a very big acceleration. We'll talk about what that means a little later on, but just I'm just telling you right now, that is a very, very big acceleration. All right, moving along, we've got a key concept box to fill out, and then we'll wrap up this video. So here it is. There are 5 quantities of variables. 5 quantities of variables will be associated with each problem. What were they? They were D, VO, VF, A, and T. The key to solving big 3 problems is to identify, remember, 3 of the 5 variables. If 3 of the 5 variables are known, the big 3 can be used to calculate the remaining 2 variables. Be very sensitive to the signs of your variables. Signs will be the root of most errors. I guess unless you plug them in wrong into your calculator, it'll be errors as well there. Time will always be positive. And if you're running through all of your calculations and time comes out to be negative, you made a mistake. If time is negative, then a mistake was made. The big 3 may only be used when the acceleration is constant, which means it will always be the same. which will be the case for pretty much all the problems that we work with. If the acceleration does change to that problem, then two setups are needed to solve the problem. In many cases, the final velocity of the initial acceleration will be the initial velocity of the final acceleration, and we'll help you with that as we go along. So, big thing right now is the first 6 there, and that last bullet point we'll work it through as we work through some problems in the problem set. There it is.